So we're going to pick up this proof right where we left off. I had an interruption there, and so we're going to continue on. We had just shown that D implies A. We did that part of showing that D is equivalent to A. So now we still have another portion of this proof to work through. We must show that part A implies part D. This will be part 2 of the proof. And we're going to use some logic here. We're actually going to apply we're going to go through an equivalent process. So for our part 2, we're actually going to show that not D implies not A. That's something called the contrapositive of the original statement. And that's equivalent to showing A implies D. We're going to assume D is not true. And we're going to show that implies that A is not true. And that's actually logically the same as showing that A implies D. So if we assume D is not true, then A does not have a pivot position in each row. And let's see, we want to show that A is not true. So we want to find a B so that AX equals B has no solution. So we can row reduce A to U just as we did before. When we row reduce A to U just all by itself, the last row of U must be all zeros. Because if it wasn't, then we would have a pivot position in that last row. So if A does not have a pivot position in each row, when we row reduce, we're going to get a row of all zeros that we would put at the bottom of our reduced matrix. We can pick a column vector D with last entry equal to 1. It could be all zeros in a 1, could be anything in a 1. D is in our M, so it has M entries. Its last entry is 1. Now why am I doing that? Because then UD, so the matrix I get by taking the columns of U followed by the column D, has D as a pivot column. So UD represents an inconsistent system. A system with no solution. We can reverse the row operations. And so pass from the matrix U, D, that augmented matrix, we can change back to a something else. Whatever this turns into, I'm going to call B. So I'm just going to say D changes. And AB must also represent an inconsistent system. Because when we pass through row operations, the solutions to the corresponding system stays the same. So no solution stays no solution. So there is some B in Rm such that Ax equals B has no solution. This means A is not true in this case. So we have shown that not D not true implies A not true. So part 2 is done, and therefore A must be equivalent to D when we combine our part 1 and part 2 arguments. Theorem 4 is proved. Now, it's okay if you're like, what? I don't expect you to be able to repeat those steps. I just want to be able to go through that so you could see what a formal kind of proof argument would be in this situation. You are not responsible for this proof, but you will be responsible for using Theorem 4. I want to just briefly mention Theorem 5, which is much easier and sort of something we would take for granted. It's our closing remarks here on this section. If A is an m by n matrix, comma, if U and V are vectors in Rn, and if C is a scalar, then the following is true. A times the sum of U plus V is equal to A times U plus A times V, and B, A times C times U is equal to C times the product of AU. So these are sort of like, one of them sort of like a distributed property of the multiplication of a matrix times vectors involving, it's distributing over vector addition. The second is sort of an associative property situation where we can, it's almost like we can factor a scalar multiple out in front of matrix multiplication times a vector. The proof, I'm not going to go through because I've done enough proof here. I'm going to say just see page 39 of the textbook. The proof of this theorem is actually much, much more straightforward than the proof of theorem 4. It's not nearly so abstract, so I do suggest you try reading this. I think it's something you could reproduce, you definitely could follow. And that's it for 1.4.